Brad, let's jump into a little more challenging of a problem, a little more nutty. Lots of algebra, a lot of prior knowledge, and some current knowledge. So there's our definition again, and that's what we're going to be using to find the region bounded by the graphs of an f and a g. So here it is, and they call it the compound region. Let's take an example. It's example 2, straight from your textbook. So if you want to go look, this is it. So we want to find the area bounded by the graphs of f and g. And notice that it does not give us any bounds. That's because there's some sort of area trapped between these two things. So let's just draw it up really quick. Like on tests, I'm not going to be giving you graphs of things. So you're going to need to know. All right, so first we have our f of x. And we can see that its leading term is a square, and it's got a negative in front of it. Therefore, it must be a parabola facing down. Those are some things that you must know. If you don't know if you can't recognize what's a parabola, you might have some issues with this class, because we have to know our parent functions. You got to know what things look like. So from that information, you can see that, it is a parabola facing down, and that we have a y-intercept at 6. We could take a quick derivative on this thing to find out where the vertex is, because does it go this way? Does it go this way? I mean, which way does it go? And, well, that's simple. You just take a derivative on it and set it equal to 0. Isn't that negative 2x plus 3? Set equal to 0, and you find out x equals 3/2 is the vertex. Therefore, it's just some sort of parabola that's doing whoop, this. You don't have to be perfect. And you don't have to graph all of these. As a student, hey, I didn't graph any of them. I just knew what my parent functions looked like. I would be able to recognize this parabola facing down, and then we got something else. I would assume, because we have to know what's on top and what's down below. You'll see in a second. So there was a little quick trick to figure out where the vertex was, to find out what the shape of the graph is. And then next we move on to our g of x, and then, the absolute value is not your friend any longer. So we all know how to graph an absolute value, don't we? It's just a v. All right, just looks something like that. So now we can see that there is some area trapped in between the curve and our absolute value. So in order for us to find this area, we have to go from a to b, and it doesn't give us any a's to b's. We have to find that ourselves, of our function minus our other function. And we can see that the f of x is on top and the g of x is down below. Just because one's called f does not mean it's above. Just because one's called g does not mean it's below. You have to be able to figure it out. It's one of the tricks. So now we need to know, what is this a value? What is, and I'm going to move this thing a little bit. Sorry, I made my 3/2 a little close. Put it over here. It's our b value. Because the b is not at the vertex. I didn't draw it perfectly. It's not to scale. Nothing I draw is to scale. But there we go. So let's figure out what our a and our b is by setting them equal to each other. So do we just do this? Just take your f and then just set it equal to the absolute value of 2x? Tell me how that works out for you. Let me know how well that works for you with that absolute value. You just treat it as positive and just be done with your day? Absolutely not. Now, hopefully you've learned this throughout algebra, throughout Calculus 1. If you took Calc 1 with me, I sure as hell hope you know this. I feel like I'd be a bad teacher if not. But we need to know how the absolute value works. Do you know how the absolute value works? Do you know what it's equal to? When it's just, say, like a 2x and ax, just an x. It's a piecewise function, saying that if you have positive values of x or 0, well, you could just take the absolute values off. All right, you plug in, say, x equals 4. 2 times 4 is 8, and yes, that would be the absolute value. Oops, sorry about that. If your x values are negative, it says you'd have to change the sign of the interior, right? So if you plug in -4, you have 2 times -4 is -8. The absolute value of -8 is +8. You change the sign. So it doesn't mean it's negative, it just means that's the line. So what we have is on the left-hand side of this graph, you have y equals -2x. On the right-hand side of the graph, graph, you have y is equal to positive 2x. So it's actually two separate functions. So what we're going to do is we're going to take our negative 2x and our f of x, and we're going to set it equal to each other to figure out what our a value is. What is that negative value of a? So we'll take our f, negative x squared plus 3x plus 6, and set that thing equal to not positive 2x, but negative 2x, because we're looking at the left-hand side. Let's bring everything over to one side. This breaks a rule for me because there's a negative leading coefficient, but I want to take this step. So we'll add this over, and we get positive 5x plus 6 is equal to 0. Now I'm doing that because this might pop back up again. You might see it a little bit later. There's some patterns that I want you to start seeing that emerge. All right, now I'm going to factor out the negative. And then we'll just factor this thing out. What is that? Minus 6, positive 1. Oh, and I also divided by negative 1 really quick. All right, just got rid of that. Because we're not going to use leading coefficients that are negative. So we got x is equal to 6, or x is equal to negative 1. But since we're looking at the left-hand side, x equals 6 is not an answer. It's x equals negative 1. That's what our a value is. That's where our point of intersection, well, the value of the x on the point of intersection. So x equals negative 1. Now we're going to need to look at our right-hand side. And that's going to be with a positive 2x. So we take our negative x squared plus 3x plus 6. And then we're going to set it equal to positive 2x. Now let's move everything over to one side. Let's set it equal to 0. We subtract that out. We get a positive x plus 6 is equal to 0. I'm going to leave that there once again because there are some things that you might notice. You might see. I don't know. Just throwing it out there. All right, so let's once again, we're going to factor out the negative. We're going to divide by that negative 1, and then we're going to factor. What is this one? Minus 3, positive 2. Yep. So we get x equals 3 or x equals negative 2, but we're on the right-hand side, so it can't be negative. It has to be the positive. So we have now found our b. Whew. So you wanted to take calculus, huh? So we have our bounds. Cool. So now that we just run right through and just do it? No. There's a big issue. This problem just has all kinds of little issues here where we have to go back to the graph and see that we have to break this into two separate pieces. We need to find the area from negative 1 to 0. And then we're going to have to add that area from 0 to 3 because we have two separate gosh darn functions. The absolute value is not your friend. So let's start working on it. Let's go get our area. I'm going to need to move down because it's going to be long. So our area is equal to the integral from negative 1 to 0. We have to break it into two pieces. And we're going to take our f of x, which is negative x squared plus 3x plus 6. And now we have to subtract out the function on the left, which is negative 2x. And then we're going to add it to, from 0 to 3, of negative x squared plus 3x plus 6 minus the 2x. Now, not the negative 2x because we're on the right-hand side. This is the left. This is the right. All right, getting rid of that. Well, let's start putting some like terms together and let's see what's going on so we can start solving this. So from negative 1 to 0 of negative x squared. So a negative and a negative is a positive. And then we go to here from 0 to 3, negative x squared plus x plus 6 dx. I swear these sound familiar. That is not a coincidence. It's not a coincidence that once we set them equal to each other to solve, well, you might get the same thing or they might just be off by a sign. All right, let's get into it and solve. Now we got to do the woefully difficult stuff of adding 1 to exponents and then dividing by those numbers. So we have to add 1 to the 2, that's the 3, and then we divide by the number. And then we just continue on. We give the 6 just the next value, and then we go from negative 1 to 0. Next, we're going to do our x cubed over 3 plus x squared over 2 plus 6x. And now we're going to evaluate that from 0 to 3. Oh, how's your fraction, Jill? Because we're done with the hard part. Now it's just going back. We're just doing some algebra now. Not even really algebra. We're just plugging stuff in and dealing with fractions. Oh. Yes, there they are, zeros. Zeros are the best. So let's do our upper bound first. 0. Do you see it? 0 plus 0 plus 0. Why would you write it in? And now we have to go through and start plugging in these values, which are -1, -1, -1, plus, and now we move to this one. So we're going to go from 0 to 3, so we put in our top bound first. We'll get there eventually. It's a long problem, huh? And then we got to subtract out 0. Not so bad. We're almost there. We're almost there. So what do we got here? We got a negative on the outside, negative, negative. That's a positive. Oops, forgot my square. That's 5/2 minus 6. Yep. Oh, and I forgot to put my 3 in. And now we'll do this. We'll add it to. So what's that going to be? 27 over this, -9. That's 9/2. That's 18. All right, let's put it all together. Let's see what we end up with. So distribute. We got -1/3 minus 5/2 plus 6 minus 9 plus 9/2 plus 18. So what is that? 9, 15. -5/2 plus 9, that's 4/2, that's 2. Minus 1/3. So what do we got? 17 minus 1/3. Age onset dyslexia there. Telling you, don't get old, y'all. So you have 51/3 minus 1/3. You get 50/3 of a freaking unit. Oh my goodness. Oh my goodness. Look at all of that work. 12 minutes, 30 seconds into this thing, and we finally finished up this problem. But that is the reality of a Calculus 2 class. Problems can be tough. They can be long. There can be all that stuff you learn from algebra. You still need to know it, along with all this new material. It's the rough one, but you can do it if you put in this time. All right. See you in the next one.